Today we will start that capacitance of 3-phase the double circuit lines, right. So, come back to that. Earlier this thing we have seen for inductance as well as the capacitance, that assuming that lines are transposed, right. So, this is the configuration for the first transposition cycle, this is the configuration for the second transposition cycle, and this is the diagram for the third transposition cycle. So, section 1, section 2 and section 3, this arrangement we have seen everything before, right. All the distances are given, that is A, B, C, and this is A dash, B dash, C dash for first transposition cycle. Second one is your A, B, C and your A dash, B dash, C dash, and for the third transposition cycle this is A, B, C and this is your A dash, B dash and C dash, right. So, all the distances are marked here. For later also I have given that A to A C dash is D1, A to B dash is D2 and your B to A dash is D3 and B to B dash D4 and AB and B to C, this distance is equal from the symmetry. So, this is D and D, same is everywhere, right. So, these 3 sections of your 3-phase double circuit transpose line, right. Now, the distances for your understanding and everything all are marked actually D1, D2 for the section 1, section 2 and section 3. For all these cases, just for easy understanding I have marked everything, that D1 is equal to DAC dash, D2 DAB dash, D3 DAA dash, D4 BB dash and D5 is equal to DAC and capital D is equal to DAB is equal to DBC. Similarly, for section 2 and section 3 all the distances are marked, right. Now, each phase conductor is transposed within its group, right. So, within this group only conductors are transposed, right, here and here also, right. So, double circuit line it is, right. Therefore, the effect of ground and sealed wires have been neglected, right, because its effect is negligible. So, in this case per phase equivalent capacitance to neutral is CAN is equal to 0.0242 divided by log dq upon ds microfarad per kilometer. In generally you know log d upon r, right, but as it is your double circuit line, 3-phase double circuit line. So, it is basically log dq upon ds microfarad per kilometer. This is equation 35 and this we have seen before, right. Next you have to calculate DEQ and DAS. You have to calculate DEQ, just hold on, you have to calculate DEQ and DS, right, these two you have to calculate. So, in this case first DEQ you know earlier we have seen for inductance also, that capacitance also same thing, DAB into DBC into DCA to the power 1/3, right, and DS is equal to self given DSA into DSB into DSC to the power 1/3. This equation is marked as 36 and this is 37, right. Now, DAB is actually DAB is DAB AB dash, DA dash B dash, DA dash B. Just one I am showing that your DAB is equal to A to B, that means that is your DAB, then D your AB dash, so DAB dash, then your DA dash B dash, so DA dash B dash and DA dash B and DA dash B, right. This to the power 1/4, right, because 4 distances are there. So, basically from the symmetry is equal to D into DD2 into D into DD2 is equal to DDD2 to the power half, right. Similarly, you calculate DBC, right, DBC also will become DDT to the power half, right, ABBC from the symmetry you can write it will be half, but AC will be DABBC CA will be CA same thing, CA will be same thing DCA dash, just take all the 4 combinations here, right. So, DCA dash, DC dash A dash, right, and C dash A from this transmission cycle 1 only, from this figure only, right, to the power 1 by 4. That is actually will come d 5 into d 1 into d 5 into d 1, that is actually d 5 square d 1 square, so is equal to d 1 d 5 to the power half. So, d a b d b c d c a, you have got it. Now, this d a b d b c and d c a you substitute in this expression, that is equation 35. If you do so, so d equal will come d dt to the power half into d dt to the 1 half into d 1 d 5 to the power half and whole to the power, they are all these things to the power 1 third, that is 1 third. So, is equal to, it is d to the power 1 third, then d 2 to the power 1 third, then d 1 to the power 1 by 6 and d 5 to the power 1 by 6, right. So, this is actually equation 38, right. Similarly, DSA, if you take the self one from the symmetry only, right, R into D 3, because your what you call DSA will be R into D 3 to the power half, DSB will be your this thing R D to the power half, and DSC will be R D 3 to the power half, right. Just 1 minute. So, from the your what you call from the symmetry, you can make all this your what you call all the calculations, right. So, it is because if you take 4 combination, R D 3 into R D 3 will come to the power 1 by 4, ultimately it will be R D 3 to the power half, DSB will be R D 4 to the power half, and DSC will be R D 3 to the power half, right. So, next is, once you get DSA, DSB and DSC, all these things you have got, right, then your DS will be DSA, DSB, DSC to the power 1 third. So, substitute all these 3 expression, right. If you substitute, then your this one will be DS is equal to R D 3 to the power half into R D 4 to the power half into R D 3 to the power 1 third. So, it is coming actually R to the power half, then D 3 to the power 1 third, D 4 to the power 1 by 6. This is equation 39, right. So, if you see that the transposition cycle, the DEQ and DS will remain same for section 2 and section 3, only conductor is changing position, but configuration remains same, right. Therefore, for the second and third case also DQ and DS will remain same, right. So, therefore, substituting the DEQ and DS in equation 34, that means this equation, that means your if you substitute this equation in 34, right. So, you can get CAN is equal to 0.0242 log all this expression. After simplification, it will come this much microfarad per kilometer. So, this is that for equation 40. So, this is basically one phase to neutral, right. It is a balanced system. So, BN, CAN, CBN, CCN, all the values numerical, all the expression will have the same values, right. So, this is that line to neutral capacitance for the 3 phase double circuit line. This is the expression, right. You need not remember anything, because it is almost impossible to remember, but because all this D 1, D 2, the way it has been taken, you can take different way, different terminology will come here, different your that nomenclature, whatever you take, it will come. So, better is that you have to derive that, and then you find out what is the value of this capacitance, right. Now, another thing is that next one is that effect of earth on the capacitance, right. So, this is effect of earth on the capacitance. Say this is your that earth plane, assuming that this is 0 potential, and you have a conductor here, right. A uniform charge is uniformly distributed, right. Charge is, assume that this is a positive charge, right. So, this is a single conductor earth plane, 0 potential here, and we will use that introduce Kelvin's, that your what you call that image charges. So, the effect of the presence of earth can be accounted for the method of image charges introduced by Kelvin, right. So, this one figure 8a shows a single conductor with uniform charge distribution and with height h that above a perfectly conducting earth plane. That means, this conductor is above the ground, that height is h actually, right, and we have to include that your how to call the effect of the earth, right. Now, what one can do is that we will make it a image conductor. Just suppose this is a charge q, say they will take another image conductor whose if it is a plus charge q, then it will be minus q, and if it is from here to here it is h, we will imagine that it is also below the ground, it is also here at height h. So, total height is from here to here is 2 h, right, and this is actually Kelvin has introduced this concept, right. So, if we assume that this conductor, right, this one, it has has a positive charge q coulomb. If this has a q coulomb, then an equal amount of negative charge minus q coulomb is induced in induce the earth. That means, it is here. We will assume if it is a q, then here it will be a minus q. Another thing is the electric field lines will originate from the positive charge, right, that is right, and on the conductor and terminate on the negative charges. That is why it is made like this, right, originating from the positive charge, assuming this is a positive charge, and terminating here at the negative charge, right. So, that is, and figure 8b, that means this one, figure 8b, that means this one, earth plane and image charge of one conductor, shows that the earth is replaced by image conductor lies directly below the original conductor, right. So, the electric field above the plane is the same, that is, I mean whatever is the electric field above here, here also it is same. That means, if you try to take potential between any two points above this, right, here we assume that they are same actually. That is why I made it that electric field above the plane is the same as it is when the ground is present instead of image conductors, right. Therefore, the voltage between any two points above the earth is the same as in figure A and figure B, right. So, what any two point you take, whatever the voltage will be here, here also yes, this thing above this plane, that anywhere the any two point, the voltage will same point, of course, voltage will be same, right. There, so this is that considering this image conductor, we have to find out what is the effect of the earth on the this thing, what we call on the capacitance, right. So, to derive such thing, for example, that capacitance of a single phase line considering the effect of earth, right. So, we will show here only the single phase one, 3 phase one we will be leaving up to you to do this, right. So, we are assuming that a single phase line having their radius r, right, and there are two conductors. If charge is here q1 is equal to q, then naturally here q2 will be minus q, right, and this image charges, if it is q1 is equal to q, here will be minus q. So, we are taking q3 is equal to minus q1 is equal to minus q, image charges. This is the image charge of this one. Similarly, for this one, image charge of this one is this one, this is the earth plane, here it is q2 is equal to minus q, that means image charge will be plus q. So, q4 is equal to minus q2 is equal to q, right. So, and distance between these two conductors is d, therefore, distance between the image conductor is also d. From the ground height is h. So, this side is also h. So, total is 2 h, right. So, first you have to find out the potential difference between conductors 1 and 2, and you have to apply the equation 5. Earlier we have given equation 5, I am writing it once again, right, for your this thing. So, this is for your 4 conductors effectively, because this is of course, this is that this is 2 conductors single phase, but 2 image conductors are there. So, you have to consider the 4 conductors. So, if you apply equation 5, then generally what will happen, the voltage between this 1 and 2, these 2 conductors V 1 2, you can write, you apply equation 5, right. If you go back to equation 5, just let me see if I can quickly find out equation 5. Just 1 minute, just hold on. This equation 5, this is actually equation 5. It is general formula Vki is equal to 1 upon 2 pi epsilon 0, that m is equal to 1 to n qm ln dim upon dkm volts, right. So, here 4 conductors are there, including 2 image conductors. So, n is 4, right, and you have to find out k is equal to 1, I is equal to 2, that is V12. So, here your here same 1 upon 2 pi epsilon 0, m is equal to 1 to 4, and here it is equal to k is equal to your 1 and I is equal to 2. That means, if k is equal to 1, it is d1m, if I is equal to 2, d2m, right. Therefore, this equation becomes, equation 5 becomes 1 upon 2 pi epsilon 0, m is equal to 1 to 4 qm ln d2m upon d1m. Now, you expand this, right. If you expand this, it will come V12 upon 2 pi epsilon 0 q1 ln d21 upon d11 plus q2 ln d22 upon d12 plus q3 ln d23 upon d13 plus q4 ln d24 upon d14. This is equation 41. Now, d11 is equal to dt2 is equal to r, the radius of the conductor, right, and d12 is equal to, and d12 is equal to d21 is equal to d, because compared to r, d is very large. So, that is why d12 is equal to d21 is equal to d. Now, d23 and d14 they are equal, that is d23 I mean this diagonal one and d14, this diagonal one and this diagonal one, d23 and d14 is equal to, this is basically under root d square, and here it is 2h. So, under root d square plus 2h whole square, that means root over d square plus 4h square, right. That is why d23 is equal to d14 is equal to root over 4h square plus d square, right, and d13 is equal to d34, d13 is equal to 2h is equal to d24 is equal to 2h, that is d13 is equal to d24 is equal to 2h, right. Now, here everything is defined, here everything q1, q2, q3, q4 all are defined. Therefore, q1 is equal to q, q2 is equal to minus q, q3 is equal to minus q, and q4 is equal to q. So, all these things you substitute in equation 41, here you substitute and simplify, right. Therefore, your V12 is equal to after substitution it will come like this, V12 is equal to 1 upon 2 pi epsilon 0 q ln d upon r minus q ln r upon d minus q ln root over 4h square plus d square divided by 2h plus q ln 2h root over 4h square plus d square, right. So, therefore, V12 is equal to 2 pi epsilon 0, it will come up after simplification 2 q ln d upon r plus 2 q ln 2h root over 4h square plus d square. Therefore, V12 is equal to your q by pi epsilon 0 ln 2 dh divided by r root over 4h square plus d square, right. So, these two and these two if take common, these two will cancel, these two. So, and if you it is ln and ln, so it will be basically 2 dh divided by r root over 4h square plus d square, right. Therefore, V12 is equal to q by pi epsilon 0 ln d divided by r in bracket 1 plus d square upon 4h square to the power half volt. This is equation 42, right. So, this is the voltage thing. If it is, if earth effect is not there, ground effect is not there, then earlier it was just d upon r, but now it is r into 1 plus d square upon 4h square to the power half. That means, this factor has been multiplied with the r, right. Therefore, C12 is equal to q upon V12, right, is equal to pi epsilon 0 divided by ln d upon r into 1 plus d square upon 4h square to the power half farad per meter. This is equation 43. Now, you convert it to log, then instead of natural log, then C12 is equal to 0.0121 divided by log d upon r into 1 plus d square upon 4 square to the power half microfarad per kilometer. This is equation 44. Now, in equation 44, it can be observed that the presence of the earth modifies the ratio r to r into 1 plus d square upon 4 square to the power half, right. So, earlier when effect of earth was not there, it was r only, but now with this r a factor is multiplied, that is 1 plus d square upon 4 square to the power half, right. However, this d square by 4 square term actually is very small, right, and hence the effect of earth on line capacitance is negligible. Actually, this term, this d square by 4 square, actually it is because conductor lies much above the much above the ground, right, compared to this d, because d is the spacing between the two conductors and h is that height of the conductor from the ground. So, d square upon 4 square will be much smaller, right, that is why its effect is negligible. So, this is for your what you call, this is for your single phase line. So, for 3 phase one, I will suggest that you should try yourself, right. Now, come to that example, right. So, this is a figure 10, the 3 phase bundle conductors, right, 3 phase bundle conductors. So, figure 10 shows a completely transposed 50 hertz 250 kilometer long 3 phase line has flat horizontal phase spacing with 10 meter between adjacent conductors, right. If the outside radius is 1.2 centimeter, that means this is the central stand and 6 more are there around that, but outside radius is given here, no question of r dash or anything, right. So, if the outside radius is 1.2 centimeter, that is given, and the line voltage is 220 kV, you have to determine the charging current per phase and the total reactive power in megavar supplied by the line capacitance, because whenever you consider that line capacitance, the charging capacitance, basically it injects actually that your reactive power, right. So, particularly for high voltage long transmission line, you have to consider the charging capacitance. So, that means it injects your what you call that reactive power. So, that means you have to find out the total reactive power in megavar supplied by the line capacitance. So, in this case, so this is the configuration that it is bundle conductors, but A dash in each phase two such conductors are there, right, A dash, B dash, C dash. So, between these two distance is 0.4 meter, here also it is same, and the distance 10 meter and 10 meter, right. So, what we have to do is, first the outside radius is given. So, it is already given, outside is 1.2 centimeter. So, it is a 0.012 meter, right, and this is the d is given, d is equal to 0.4 meter between these two, A dash or B dash or C dash, d is equal to 0.4 meter, right, and outside radius means you need not do anything else, right. So, directly it is given that 0.012 meter, and now you have to find out ds, right. So, outside radius we are taking r0, right. So, ds is equal to r0 into your r0 into d root over, right. Actually if you what you call if you try to find out that what will be ds, right, in general. So, basically it is your ds is equal to your r0 into d into r0 into d to the power 1 by 4, right, 1 by 4. Basically it is dA into dA dash, then dA dash into your dA dash A, right. So, basically it is r0 d to the power 1 by 4. So, that is your r0 d to the power half, right. So, that is why ds is equal to r 0 root over this one into 0.4. So, it is 0.00693 meter, right. Now, DEQ earlier we have seen DAB into DBC into DCA to the power 1/3. So, from the symmetry of this configuration, DAB will be is equal to DBC, right, but DCA will be different, right. So, DAB is equal to take all the possibilities, the DAB, that is distance DAB into DAB dash, then DA dash B into DA dash B dash, right. So, that way it will be your DAB is equal to A, here center to center is given, middle point rather, middle point midpoint of these two conductor and these two is given, that means DAB actually is equal to 10 meter, right. I mean A to B is 10 meter, right. Therefore, DAB is equal to your 10 meter and DAB dash D A to B dash, right. A to B dash means A to B is 10 meter and B to B dash is 0.4. So, therefore, DAB dash is equal to 10.4, right. Similarly, DA dash B, if you take DA dash B, that is your here to here A dash B, right. So, from here to here it is your what you call, this is your center to center is 10 meter. So, this you have to find out A dash to B dash. So, from it is midpoint. So, this is 0.2 and this is 0.2. So, it will be 10 minus 0.2 minus 0.2, that is your 9.6. That is why it is d A dash B is equal to 9.6 and again d A dash B dash, again same thing, A dash B dash again 10 meter. So, it is into 10 to the power 1/4 because 4 distances are there. So, it is equal to 9.995 meter and DBC is equal to DAB is equal to 9.995 meter, right. So, similarly, your DBC is equal to DAB, both are same from the symmetry AB to BC same. Now, you calculate, similarly you calculate DCA. So, if you calculate DCA, it will be DCA into DCA dash, DC dash A into DC dash A. Similarly, all the distances DCA will be find 20 from this figure, you will find that DCA is equal to 20 meter, then DCA dash 19.6 and DC dash A 20.4 and DC dash A dash in 20 to the power 1/4 is equal to 19.997 meter. Next, you calculate DEQ is equal to 9.995, right, into 9.995 into 19.997 to the power 1/3, that is equal to 12.594 meter, that is DEQ, right. But if you see that approximate values for DEQ can be calculated quickly, which is very close to exact value. If we assume that neglect all these things, if we assume that instead of subtracting this 0.4 and this that, if you take 10 into 20, I mean if you look at the diagram, that if we take that this is 10 and between these two 20 if you take, then you will find that 10 into 20 1/3 is equal to 12.599 meter and this one we got actually this one 12.599 and this one you got 12.594. So, 599 and 594 there is almost no difference, it is approximately 12.6 meter, this is also approximately 12.6 meter, hardly any difference, but from the classroom purpose or numerical purpose you have to solve this, but from the research purpose you can take this one, right. So, that is your that is no difference almost, right, but you have to see that your approximately they are same. But anyway, if you apply now equation 34, CAN will be 0.0242 divided by log DEQ upon DS microfarad per kilometer. You substitute DEQ and DS here, all this, you will get CAN is equal to 0.0100796 microfarad per kilometer is equal to, if you write in farad, 2.677 into 10 to the minus 6 farad, right, because that your line length is 250 kilometers. I think when we took that line length is 250 kilometers, right. So, it is your microfarad per kilometer, that this value you have to multiply by 250, right. So, that will be your 2.677 in 10 to the power minus 6 farad. Now, charging current I is equal to j omega C n into V line to neutral voltage, because you are taking C A N, that line to neutral capacitance, right, into V. L stands for line to neutral voltage, and J the capacitance in your generally is inject leading current. So, j omega C A N V L N. So, magnitude of I charging is equal to j will not be there here, because it is magnitude omega C A N V line to neutral. So, V line to neutral, if V A N is the reference phasor, then it will be V A N angle 0. Therefore, V mod V L N is equal to magnitude V N is equal to 220 upon root 3 kilovolt, right, because line to line voltage was given 220 kV. So, 220 upon root 3, because you need line to neutral voltage V L N, right. Then the magnitude of charging current, right, magnitude of charging current here is equal to 2 omega 2 pi f into 2.6777 10 to the power minus 6 into 220 by root 3 kilo ampere per phase. That is I charging current will be 0.1068 kilo ampere per phase, right. Now, QC 3 phase is equal to omega C n into V line to line voltage square, right. So, basically it is V square of, in general, V square upon XC, XC is equal to 1 upon omega C. So, here also it is equal to V line to line square by your XCN, right. So, that is actually 1 upon omega Cn, it will go to the your what you call numerator. So, omega Cn into VLL square, substitute omega 2 pi f, your Cn also 2.67 10 to the power minus 6, and VL is 220 whole square megavar, right. This is actually 40.70 megavar. So, this much var is injected. Okay, thank you.